Can you hear me? Okay. Now, first thing is you should never clap before a talk because you don't know if you're going to hear a good talk or not. So, first of all, I would like to thank the organizers, Charling Tao, Shudemav, for the kind invitation to give this lecture. And I would like to thank all of you for coming out. Now, it is Friday night, and North American students would not be in a lecture hall on a Friday night. They would be out partying. Okay, so I'm surprised to see so many students here. Now, maybe you are under the impression that you're going to get a nice, entertaining talk. You're not going to get a nice, entertaining talk. I'm going to try to make you learn. And the problem is that I was speaking too long, and so the computer froze on me, and hopefully it will come back. Yeah, it will come back. Good. Now, you may also think that you will get an answer to the question that I'm asking here. What was before the Big Bang? I'm not going to answer that question either, but hopefully you will walk away from this talk seeing this question in a very different perspective. Most importantly, I want you to walk away from this talk knowing that cosmology, early universe cosmology, is an exciting field. So, what do I want to do? First of all, I want to explain what cosmology is, what early universe cosmology is. Now, you see, to do early universe cosmology, you do need a framework, and I'll have to teach you about this framework. And this framework involves space and time. It involves a cosmological model. So I'll have to teach you a little bit about the theory of space-time, which is Einstein's theory of general relativity. Okay. Now, this standard Big Bang cosmology, which you can read in old textbooks on cosmology, is insufficient. It cannot explain the questions that we would like to explain in cosmology. So we need a new cosmology. And this is the inflationary cosmology. And to develop that, we need a little bit of help from a friend. And the other friend is the particle physicist. Okay? But as I'll try to convince you, this current model of early universe cosmology is not sufficient either. It has some problems, which I'll try to convince you of. In particular, one of the problems is that we cannot answer the question, what was before the Big Bang? So we have to do better than what is being done here. So we need the help of another friend, and this friend is a superstring theorist. Now, superstring theory is a theory in development, but I will try to teach you a little bit about superstring theory. And I'm not a string theorist, so in order to teach you a little bit about superstring theory, I need help. And help means demonstration devices. And this is what I want you to think of as a superstring, like a hairband, like an elastic band. I will use that when I get to this. And I will need another prop, and this other prop is this piece of paper, which will be representative of space. And I will talk about the interaction of the strings with space, and this will give me a new view of cosmology. And in terms of this new view of cosmology, the question in the title of this talk will appear in a different light. So this is what I want to do. It's ambitious. I want to teach you a lot of things. So you'll have to pay attention. So what is cosmology? So the goals of cosmology is to answer several questions. One of the questions is the question in the title of this talk. Questions about the origin and early evolution of the universe. What is the Big Bang? Was there a Big Bang? What was before the Big Bang? Those are philosophical type questions. But cosmology has other goals which are much closer to the heart of physicists or quantitative scientists. We want to explain the observed large-scale structure of the universe. Now, for those of you who are not astronomers and not cosmologists, I want to give you some pictures of what I mean by large-scale structure of the universe. So as scientists, we have instruments. And our instruments are telescopes located in beautiful parts of the world, like here up in the Andes. This is an optical telescope. It measures the optical light that comes from the sky. And if you look through such a telescope, the first thing that you will see is galaxies. Galaxies are assemblies of many, many millions of stars. Now, from my point of view as a cosmologist, this is much too small. Millions and millions of stars, much too small. I will replace this entire galaxy by a point. And let's look deeper. This is a projection of the entire sky onto a plane, like the projection of the surface of the Earth onto a plane. And each of these dots represents a galaxy. So the universe is huge. It contains a huge number of galaxies. And you see that galaxies are not distributed in an even way. There are regions where there are many galaxies, and there are regions where there are fewer galaxies. So this is a visual impression of what I mean by structure. Now, there are other ways to probe the universe. We can look through microwave telescopes. So we build a microwave telescope, we look at the sky, and yes, there is radiation coming. Now, microwave telescopes are also located in beautiful parts of the world. For example, in the high Andes, at the South Pole. This is actually the South Pole telescope, which McGill is involved in. And there are even telescopes in outer space. So with these telescopes, you look at the sky, and you look at the intensity of the microwave radiation, which comes from different directions in the sky, and then you will find a beautiful temperature map. So you measure intensity, you infer temperature. And all these expensive telescopes and satellites provide this beautiful picture of the distribution of the microwave sky. Do you see all this structure? All this structure? Perfectly isotropic. You look in any direction in the sky and you have the same temperature. Why? Tremendous mystery. Well, so the temperature that you measure is a very small temperature. It is 3.6, it is 3 degrees above absolute zero, which is even cold by standards of Harbin or of Montreal. So now if you look a little bit closer at these maps with much greater resolution, with resolution of 1 part in 10,000, then you start seeing structure. You start seeing regions where the temperature is slightly larger, regions where it's slightly lower. So this is a beautiful map. You can post it in your room, and it will look nice, like a painting. But what the scientists do, the scientists will stick this map into a statistical black box. And the statistical black box will produce a boring graph. Well, it's in data points. Okay, what does this plot mean? This is scale, angular scale, and this is a measure of the structure. So if there were no structure in the microwave background, then the curve would be 0 everywhere. So this beautiful map has structure that we can quantify. And, well, you see data points. At small angular scales, there's some statistical errors. But here, the precision is quite good. There's some systematic error here for very large angular scales. So I asked an artist to draw a curve through these data points that will fit the data fairly well. And this is the red curve which the artist drew. And I will tell you the name of the artist later. There are actually 2 artists who participated and who drew independently a curve like this. Okay. So this is the goal of cosmology, is to explain this large-scale structure, which we can quantify. Where does this come from? But this is not where cosmology ends. A good model of cosmology needs to make predictions for what we will see in the future with better telescopes. So these are the three goals of cosmology. There are some deep philosophical questions. There's some solid science. We want to explain things that have been observed. And then we want to make predictions for future observations. So we want to be able to be falsified. And this, to me, is a very exciting combination of questions. Okay. So in order to develop cosmology, we need a framework. So I have to tell you that the framework will involve space-time, and it will involve a model which is built on space and time. So what is the universe? The universe is space and time, but it is not only space and time. It is also matter which lives in space and time. So what do we use right now in cosmology? We use space and time not described by Newtonian physics, but described by Einstein's theory of general relativity. So I want to explain, I'll be explaining you the basic idea of that. Now, matter in standard Big Bang cosmology is described by, well, matter is always described by physics, the physics that you learn in physics classes, either in high school or in university. And more specifically, on large length scales, matter is described by classical physics, physics that you can explore in laboratories, here in physics laboratories at university or in high schools. But on smaller scales, you actually need quantum mechanics to describe matter. Well, and on even smaller scales, you need to go to the basic constituents of matter, and that is where superstring theory enters. Maybe. Okay. So let's develop this a little bit. Space and time is dynamical. It is no longer absolute and unchanging as in Newtonian theory. And matter curves space and time. These are the two ingredients in Einstein's theory of general relativity. So this is a picture of how you should visualize this. Here you have a large mass, and here you have a smaller mass. And this sheet represents space. Now, according to Einstein's theory of relativity, mass curves space. It actually curves space-time. So this big mass will cause an indentation in the sheet of space. The small mass will feel that the space is curved, and therefore the small mass will move in a trajectory which is not a straight line according to Euclidean geometry. So this is the first building block of cosmology, the theory of space and time. Now, this is what matter does if you have a compact block of matter. It will cause a local distortion of space. But if you have matter distributed everywhere uniformly, then you can't have a distortion of space here relative to here, because here is equivalent to here. What Einstein's theory tells us is that in this case, when matter is homogeneously distributed, then space will expand. It will become bigger in time. So space with a homogeneous distribution of matter cannot be static. It must expand. So how should we visualize this? So let's imagine space as a raisin bread. So the dough is space. The raisins you should visualize as galaxies. Now if you stick this raisin bread in an oven, then the dough will expand, and therefore the raisins, even though they are at rest in the dough, each raisin will think that the other raisins are moving away from it. And raisins which are close by will think that the close-by raisins are moving away slower than far-away raisins. So Einstein's theory predicts that the further away an object is from our galaxy, the faster it will appear to move away from us. So if Einstein is right, we should be able to measure this. And this is the data. This is the apparent velocity of objects away from us. And this is the distance from us. And, well, the error bars are still quite big, but you see a roughly linear relationship. So we know that in terms of galaxies, clusters of galaxies, Einstein's theory is a good description of space and time. Now, Einstein's theory is one ingredient of standard Big Bang cosmology. The other ingredient is a theory of matter. And in standard Big Bang cosmology, which was cosmology before 1980, matter was described in terms of classical physics, which you learn in courses. Well, matter has two components. It has cold stuff, like galaxies, and it has hot stuff, like radiation, the microwave radiation. So standard Big Bang cosmology is based on these principles. What does standard Big Bang cosmology predict? The universe is expanding now. In the past, it was hotter and more dense, and therefore it was expanding faster. And therefore, at a finite time in the past, the temperature was infinite. And this is what we call the Big Bang. So standard Big Bang cosmology predicts that there was a finite time back, a point where the temperature was infinite. But what is a Big Bang? And what was before the Big Bang? Now, okay, does this theory make sense? A theory which predicts this kind of stuff. So, to be taken seriously, a theory must have had some predictions, not just postdictions. And standard Big Bang cosmology made spectacular predictions. So let's roll the universe forwards in time according to standard Big Bang cosmology. So according to standard Big Bang cosmology, the universe began as a homogeneous and very hot fireball. It was initially a plasma. Space expands, the plasma cools. About 30,000 years after the beginning, cold matter starts to take over from radiation. About 300,000 years after the Big Bang, the universe has cooled to the point where hydrogen is stable. And at that point, the universe becomes transparent to light. Electrons and nuclei fuse to form atoms. That releases light, radiation. So standard Big Bang cosmology, when it was developed in the 1950s, predicted that there should be a radiation bath coming to us from this time. And it will have been redshifted. Its wavelength will have been expanded such that the wavelength is now in the microwave region. So standard Big Bang cosmology predicted a microwave background. This existence of the microwave background was not known at that point. In fact, the famous Russian physicist Zeldovich, when he heard about this Big Bang theory, he said, this is a crazy theory because it predicts the microwave background, and there is no microwave background. Then the microwave background was discovered in 1964 and 1965. What I want to stress is that standard Big Bang cosmology made a prediction, a successful prediction. And it was not just one number. So, anyway, this is a standard Big Bang picture. There was some explosion, Big Bang. 300,000 years after the Big Bang, the microwave background was released. It travels to us and it is detected by telescopes. Now, what is the quantitative prediction of the standard Big Bang? So let's take this microwave radiation and let's let it pass through a prism. We separate the radiation into its frequency components. Now, the standard Big Bang model predicts that the microwave background is emitted as a black body, a very specific relation between intensities at different frequencies. So a black body is this following curve. It is intensity as a function of frequency. This is a textbook black body. This is what the standard Big Bang model predicts. It's not just a number, it is a curve. This is what it predicts. This is not a theoretical curve. This is the observational curve. And the error bars are smaller than the thickness of this line. So standard Big Bang cosmology made a spectacular prediction. But now as scientists, we should not just go out and party. We should ask, does the theory make sense? Will it fail somewhere? Well, are there other questions that we would like to answer? Well, for one thing, these questions are left unanswered. Well, maybe you're not interested in these questions. Even if you're not interested in these questions, there are many things about the universe which the standard Big Bang does not explain. Now, I'm not very good at computers, so this is a fairly poor illustration. The standard Big Bang model does not explain why the microwave background is isotropic. This beautiful picture which I showed at the beginning of the isotropic temperature of the microwave background has absolutely no explanation in standard Big Bang cosmology. And this is illustrated here. This is time. This is space. This is the time when the microwave background is released. We are sitting here looking at the microwave background. The microwave background has traveled for a long time between when it was released and when it hits us. And we see the same temperature here and over here, the other side. Exactly the same temperature. Can this be explained? Well, according to what you learn in physics, nothing travels faster than the speed of light. So this is the distance that light can travel between the Big Bang and the time when the microwave background is released. So, in standard Big Bang cosmology, no physics could have told this point to have the same temperature as that point. So the standard Big Bang cosmology, even though it predicted the black body nature of the microwave background, it cannot explain the fact that the temperature is uniform. Well, it cannot explain where any of the structure that we observe in the universe comes from. So, we need to do better. We need to throw away the standard Big Bang model and replace it by something else. Or, at least we need to supplement the standard Big Bang by something better. And this is where we need the help from the particle physicist friend. And the particle physicist friend tells us that at high temperatures in the early universe, physics cannot be described as a classical fluid. Quantum mechanics enters. Matter is actually has wave-like features. So, quantum mechanics and particle physics gives the right description of matter. So we need to replace classical matter by a modern description of matter to get a better theory of cosmology, of very early universe cosmology. Okay. So, according to particle physicists, we should replace matter, classical matter, by quantum matter, and this is by quantum fields. Quantum fields. Now, you're probably scared of quantum fields. But you shouldn't be scared of quantum fields I can easily explain to you what a quantum field is. I'll give you a toy model of a quantum field. Let's imagine a table, and at each point on the table you have a pencil standing upright or standing at an angle, and you connect the tips of the pencils by springs. I will call the angle of the pencil with respect to the vertical, I will call that phi. And this depends on space, and the pencil can move in time. This is a quantum field, classical field, which we then quantize. So don't be afraid of fields. Okay? So, fields. Electrons are described by fields. Photons are described by fields. All particles we know are described by fields. Let's try to use these fields in the early universe. This leads to inflationary cosmology. So the idea of inflation is the following. Let's imagine that these fields give us a period in the very early universe where space expands exponentially. You all know what inflation is, exponential expansion of something, exponential expansion of space. Hypothesis. So, Big Bang, inflation begins, inflation ends, standard Big Bang cosmology takes over. This is the idea of inflation. What does that buy us? It explains why the microwave background is almost isotropic. It explains why the universe is so huge. And it explains why the universe is spatially flat. Why, if we do geometry in this room, we get results in agreement with what you learn in mathematics, Euclidean geometry. This is what inflation explains. But inflation provides a causal mechanism for generating small inhomogeneities, which we now see as anisotropies in the microwave background and inhomogeneities in the distribution of galaxies. So you see this artist, the first artist who drew this red curve in one of my first transparencies were actually Chibysov and Mukhanov, who drew this curve in the context of inflationary cosmology. So they predicted that the microwave background should have small fluctuations, which, when you stick into this statistical package, will give you this red curve. Now, Chibysov and Mukhanov did not know the height of this red curve, but at least the shape. Okay, I haven't yet told you how inflation works. I'm advertising the success of inflation. So in the same way that standard Big Bang cosmology had a spectacular success, inflationary cosmology had a spectacular success. This, not just one data point explained, thousands of data points explained. Cosmology is a quantitative science. Okay. But what is inflationary cosmology? Well, it is based on Einstein's theory as a theory of space and time, and we replace matter, no longer classical matter, but by fields. Now, it's a bit complicated here, because the fields that we are familiar with in physics, like fields associated with light, fields associated with matter that we are made up of, do not work. They cannot give us inflation. So you have to introduce something called a scalar field. This is a model of a scalar field. So mathematically, a scalar field is nothing complicated. The slight problem is that there's only one particle in nature which we know of, which is described by scalar fields, and this is the Higgs field. But the Higgs field doesn't work to give inflation. Okay, so this is the context, the ingredients of inflation. Inflation gives us a phase of exponential expansion. But in order to get this phase of expansion, we need negative pressure, matter with negative pressure. Most matter we know of has positive pressure. And this is why we need a scalar field, because it's only scalar fields which can give us negative pressure. But not any scalar field will give us inflation. This scalar field has to be very slowly rolling for reasons which I will not explain. Okay, so if you can realize inflation, then you have this timeline, Big Bang, period before inflation. This is a period where space expands exponentially, and afterwards standard Big Bang cosmology. So what happens? Let's look at light emitted at the Big Bang, just after the Big Bang. It will travel, but then once space expands exponentially, light will expand exponentially with space. So what inflation will do is it will exponentially expand the distance that light can travel, namely the horizon. Let's look at what happens to the wavelength of some structure that you see today. So this red curve corresponds to, for example, the separation of galaxy clusters. And this separation grows like space expands. But here, during this period, space is expanding exponentially. So this length expands exponentially as well. And the final curve that I will draw is a curve which corresponds to the inverse of the expansion rate. And the expansion rate of the universe is constant during inflation, and so therefore this length is constant. Okay, so this is the space-time diagram. Inflation makes space exponentially large. Now, for those of you who are physics majors and who've taken an elementary general relativity class, as homework problem, after this lecture, you should figure out why this makes space spatially flat. That I'm not explaining. But I'm going to explain you the mechanism that generates structure in this inflationary scenario. So let's imagine you start out with lots of junk before inflation, sort of stones and people and everything like that. Once space starts to expand exponentially, everything gets diluted exponentially, and you are left with matter in the vacuum state. Vacuum state. Now, Chibisov and Mukhanov realized that the vacuum is not completely empty. There is quantum fluctuations in this vacuum. So Chibisov and Mukhanov postulated that what we see today stems from the quantum vacuum fluctuations in the early universe. And I think this is what Professor White talked about in his public lecture here, or what he mentioned. So this is the hypothesis that was made. Okay. And then this gives rise to this successful prediction. Now, let's come back to the title of this talk. Big Bang. What was before the Big Bang? Well, inflationary cosmology is no better than standard Big Bang cosmology. There was a Big Bang singularity. Singularity means things go infinite. Infinite temperature, infinite density. There was a time of infinite density before inflation. No physicist ever measures infinity in the lab. If a scientist measures infinity in the lab, it means that they've made a very bad mistake. Their apparatus has blown up. Infinity is not physics. The fact that inflationary cosmology and standard Big Bang cosmology predict that there was an infinity, a finite distance in the past, just means that the theories have broken down. So therefore, these questions are unanswered not only in standard Big Bang cosmology, but also in inflationary cosmology. A more physical way, fancy way to state that is that at very, very high densities, even quantum field theory is not adequate to describe matter. Okay? So, standard Big Bang cosmology had a huge success. It predicted lots of stuff. It was inadequate because it didn't explain enough. Inflationary cosmology had built on standard Big Bang cosmology. It had more successes, but there are also things that it does not explain. It does not explain these questions, And it has other problems, conceptual problems. So where I'm heading now in the rest of this talk is the following. I'm going to first of all tell you a little bit about these conceptual problems, and then I will argue that in light of these problems, we need to work harder. We need to develop a new theory of the very, very early universe. And since we need to use the best theory of microphysics which is available. And I think this is superstring theory. So the question I will ask is, can superstring theory lead to a new and improved paradigm? Can this new paradigm be tested in cosmological observation? And if it can, this means that string theory can be tested in cosmological observations. String theory is testable. Can this new paradigm answer this question? I won't give a preview of that. So, what are the conceptual problems of our current paradigm of inflation? First of all, what is this field which gives us inflation? Why do you have the special initial conditions of the field required to obtain inflation? Then there's a problem which I highlight in red called the Transplanckian problem, which I'll illustrate in a graph. And then there's general concerns about the applicability of Einstein's theory. So this is a list of conceptual problems. So the first conceptual problem of inflation is what I call the Transplanckian problem. So now if you've paid attention, you will recognize this space-time graph. It is the same space-time diagram which I used to illustrate inflation. Horizon, the inverse expansion rate, the length scales where we are interested in explaining structure, but I added one line, this vertical line. And this vertical line is our line of ignorance. We don't understand physics on very small length scales. Now, this very small length scale may be the Planck length, or it may be the string length, but there's some small length scale where we do not understand physics. So this region here is a region of ignorance. The theories on which inflation are based do not apply here. The problem is that if you look at the inflationary model, the wavelength of structures that we currently observe, the wavelength is smaller than this scale of ignorance at the beginning of inflation, which means that we've used the wrong theory to compute how the fluctuations are generated. We need new physics to actually explain this origin. This is a Transplanckian problem. Well, there's still the question of Big Bang. There's a singularity. Now, the other problem is the following. We know that general relativity is a classical theory. And if we try to merge the quantum theory of matter and classical theory of space-time, we will see that the quantum effects of matter will produce corrections to Einstein's theory. And the higher the curvature of space is, the larger the corrections will be. Now, it turns out that the energy scale where inflation has to take place is very close to the scale where we know that Einstein's theory breaks down. So we do not know. There are serious doubts as to whether we can apply Einstein's theory at energy scales where inflation was supposed to have taken place. So this I illustrate here. There's an early universe epoch where the curvature of space-time was large, where we again don't understand the physics. And inflation takes place very close to this zone of ignorance. So these are some of the conceptual problems. Okay. So what is the message? The current paradigm of cosmology has serious conceptual problems. We need a new paradigm of early universe cosmology. And I will use a little help from the string theorist friend. What I will do is I will try to give you just a toy model idea of what could happen if we use the help of our friend, the string theorist. It's called string gas cosmology, and you get an alternative to inflation out of this. Okay, so now you've been very patient, and I've done reasonably well in terms of time. So I've told you about general relativity. I've told you about quantum fields. So in North America, you don't learn about general relativity in undergraduate, and you don't learn quantum field theory in undergraduate. You don't even learn about string theory in your master's program. But I will have to tell you a little bit about string theory. But what I want to emphasize is that this little model based on string theory, which I will present, makes testable predictions for observations. And specifically, it makes predictions for gravitational waves, for the spectrum of gravitational waves, how the amplitude of long wavelength gravitational waves relates to the amplitude of short wavelength gravitational waves. It predicts a blue tilt, which means slightly more short wavelength gravitational waves than long wavelength gravitational waves. So, okay. String cosmology. Okay. Good. So what is string theory? String theory is a quantum theory which is supposed to unify all four forces of nature. The electromagnetic force, the strong nuclear force, the weak nuclear force, and gravity. Now, the basic objects in string theory are not elementary particles, but strings. All of the known physical theories, apart from string theory, are based on the idea that the basic constituents of nature are point particles. In string theory, the basic ingredients are strings. And you see, if you compare a string to a point particle, strings have very different features. They have internal vibrational modes, like a violin string. Strings have other features. Strings can wind space. This is space as a torus. A string can wind space. Point particles can travel on space, but they cannot wind space. So, string theory is very different from existing theories because of these basic features. Now, according to string theory, different vibrational modes of the string, of the same string, correspond to different particles, including gravity. So a single string, a single type of string, can describe all known particles. It's unification. Now there's a slight problem. String theory, superstring theory, is mathematically consistent only in 10 space-time dimensions. How many space-time dimensions do we see? 4. Well, doesn't this mean that string theory is fatally flawed? No. Be a patient. String theory predicts extraspatial dimensions. Okay. Now, the toy model of a new cosmology, which I will end this talk with, is based on taking something like the Big Bang theory. Big Bang theory is space-time, a gas of point particles. I will take space-time and a gas of strings, a gas of fundamental strings. I will assume that space is compact. I will imagine that space is not infinite, but it is compact like this sheet of paper if you would glue it together in all sides. Assumptions. Now what I'll try to do is I'll try to explore the consequences of the new stringy aspects for cosmology. the new degrees of freedom which string theory has and point particle theory does not have, the oscillatory modes. So the oscillatory modes lead to something very peculiar. You know that if you take a box of point particles and you make it smaller and smaller, the temperature of this gas of particles rises without bound. Not so if you take a gas of strings. If you take a gas of strings, initially, so you collapse this box of strings, initially the temperature will go up, but then it will reach a maximal value. You compress the box even further, temperature will go down again. You take a box of space, temperature goes up and then down again. Temperature never reaches infinity. Completely different consequences for early universe cosmology than standard Big Bang cosmology and inflationary cosmology. The fact that the temperature goes down again is related to the fact that, according to strings, physics in large boxes is completely equivalent to physics in small boxes. Okay. Now, I had hardly any equations so far. Let me at least use 3 equations. So if you take particles which are moving on a curved space with a certain radius, then the energy of particles is proportional to 1 over the radius. But if you take the length of the energy in a string, as you expand, as you make the radius of space larger, the energy of string goes up. So you replace R by 1 over R. You replace what you mean by winding, what you mean by momentum, and it's equivalent. So the fact that that strings have winding modes leads to this duality, the statement that physics in large boxes is equivalent to physics in small boxes. Totally different than standard Big Bang cosmology and inflationary cosmology. So this is what I illustrate here. This is the radius of the box, logarithm of the radius of the box. This is the temperature. You start with a large radius. Temperature goes up, temperature reaches this limiting value, temperature goes down again. Now, I will assume that the universe starts here, that we start our description of the universe when the temperature is high. That we start our description of the universe when the temperature is here. Well, what will happen here? The temperature will remain the same for a long time. I will assume that this means that space remains constant size for a long time. So in this early phase, where the temperature is near its maximal value, I will assume, well, this seems to indicate that the universe was quasi-static. So according to this simple model of strings in the early universe, the universe began in a long period with constant size, and once these strings were able to cut themselves up and unwind, space could expand. So this transition is strings being able to cut themselves up and unwind. But strings cannot have any ends. So the only way for strings to cut themselves up is for 2 strings to find each other and to intersect. Strings are one-dimensional objects. Strings in space-time are 2-dimensional objects. This is 2 strings intersecting and cutting themselves up. If you have 4-dimensional, so in more than 4 space-time dimensions, 2-dimensional objects will never find themselves. So what do? We start with all 9 dimensions of space compact like this, wound by strings. Eventually, in 3 but not more dimensions of space, this process will be possible, and then 3 but not more dimensions of space will start becoming large. The other 6 are naturally held at string scale. So, even though string theory has 9 dimensions of space, String theory applied to early universe cosmology predicts that only 3 become large. That's not a prediction, it's a postdiction. Okay. So, now remember, so this is maybe a nice numerology that 3 dimensions and only 3 dimensions become large. But that's a postdiction. We know that we live in 3 large spatial dimensions. I need to make predictions. Oh, well, I even have to show that you get agreement with the current observations. So, that's the last thing I want to do. This is the space-time diagram of inflation. The inflationary phase, standard Big Bang phase. In inflation, perturbations are created on these very small scales by quantum vacuum perturbations, because there was a phase of exponential expansion which removes all matter. So in inflation, it is natural to start in the vacuum. Well, in string gas cosmology, you don't have exponential expansion. You have a static early phase filled with strings. Vacuum fluctuations are completely unimportant. You have a thermal gas of strings, and therefore you have thermal fluctuations here. So when Professor White, in his public lecture here, tried to convince you that we all come from vacuum fluctuations, this is the scenario in inflationary cosmology, but it is not necessarily what happened. In string theory, what happens is something else. We are supposed to all come from thermal fluctuation of strings. Okay? So this is the early phase where the universe is static, so the inverse expansion rate is infinity. There are lots of thermal fluctuations here. Then the 3 dimensions we live in, they start to grow, and then we compute the thermal fluctuations of the string gas, and we compute what this implies for the density perturbations and for the microwave anisotropies. And what we find is the following. We find this red curve. And not only do we predict the shape of the red curve, we predict the amplitude. So we've done one better than inflation. So inflation with vacuum fluctuations is not the only way to get this curve. But still, this is not good enough, because this is like inflation. We've post-dicted things. Well, if string theory can do no better than explain in a different way things we've already explained, it is not much progress. We have to make predictions. So the prediction what we made is we computed the predictions for gravitational waves, and we found that the gravitational waves are produced. They are produced with a scale invariant spectrum, but with a slight blue tilt, whereas in inflation you predict a slight red tilt, inevitably. So this is the prediction we are making. So now it becomes interesting, because not only have we explained things that we already knew, that we already explained other ways, but we've made a prediction which can be tested by future experiments. And we've also explained a couple of cosmological problems along the way. What is the status of the Big Bang in string gas cosmology? Well, the universe was very, very hot and dense 13 billion years ago. It was a hot gas of strings 13 years ago. So in this sense, there was a hot primordial fireball, okay, but there was no singularity. There was no beginning of time. Time runs from minus infinity until plus infinity. So the Big Bang, the question of the Big Bang appears in a very different light if you start to go into string theory. Okay, so let me conclude. What do I hope to have convinced you of? First of all, I hope to have convinced you that cosmology is a vibrant field driven by lots of observational data, some conceptual puzzles, we've developed paradigms of early universe cosmology which made predictions, which were subsequently successfully verified. First paradigm is standard Big Bang. Second paradigm is the inflationary universe scenario. In both of these paradigms, there was a Big Bang, not only a hot fireball, but also a Big Bang singularity. But both paradigms have conceptual problems. They cannot be the full story. So this motivates the search for an improved paradigm, and I hope to have given you the flavor that superstring theory might give rise to a new and improved paradigm which will resolve the Big Bang singularity. And in this context, it is possible to observationally probe string cosmology. Now, what is the status of the Big Bang? So we know that going back in time 13 billion years, there was a very hot phase. If this is what you mean by the Big Bang, there was a Big Bang. But we do not know if there was a Big Bang singularity. In the two popular paradigms, there was a singularity, a beginning of time. But in this stringy paradigm, the situation is different. But I will leave you with the previous transparency. So thanks for your attention. So I'm happy to answer questions, or to try to answer questions.
Thank you very much, Robert.
I also think the superstring theory is very charming, but I know there is another theory called loop quantum gravity theory, and I want to ask if this theory can explain the problems such as singularity or the background, the microwave of the background. Thank you.
So my answer to that is that loop quantum gravity is not a unified theory of all four forces of nature. Now, from our knowledge of cosmology, we know that as we go back in time, all four forces tend to be equally important. And so therefore, I personally think that string theory is a more promising approach. But that's my personal taste.
Professor, I don't understand how can the vibration modes of the strings you just mentioned be considered as additional space-time dimensions?
No, it is not the vibration of strings that can be considered that are extra dimensions, but the strings live in a space-time, and mathematical consistency means that the space-time in which strings live have 9 dimensions of space and 1 dimension of time. The string vibrations, the different vibrational modes of the strings correspond to different particles. One vibrational mode corresponds to the electron, one vibrational mode corresponds to the photon. The vibrational modes do not correspond to dimensions.
Okay, there's the... Sorry, there's a person in the back first. Okay, sorry.
I want to ask a question about the dimension of our universe. Cannot be magnitude proves that the dimension of our universe is 11. An interesting thing is that many people think there should be parallel universe.
Okay, let me try. You're asking too many questions now. Let me try. To. You already asked two important questions: 11 dimensions versus 10 dimensions. Okay. Now, at one point on my transparencies, I had the statement: string theory is a theory under development. We do not have a complete understanding of string theory. We only have a so-called perturbative understanding. According to this understanding, we have 10 space-time dimensions. The 11th dimension which arises in certain descriptions, plays a different role. So we have 10 space-time dimensions. Now, the second part of your question was, what about parallel universes? My strong belief is that we are physicists. We do analysis in our universe. I don't care if there are other parallel universes or not. That's, to me, not science. There is... Okay, let me elaborate on that, because there are some fancy words. The multiverse, the landscape, these are fancy words which you might have even seen in the popular press. This is under neither mathematical nor physical control.
Next question in front.
I have two questions. The first is there any fine-tuning problems in string theory cosmology? And the second is, can string theory give rise to dark matter, dark energy, and the second thermodynamics law?
Okay, so again you asked several questions. First question about fine-tuning. Well, the situation in string gas cosmology is a bit worse than fine-tuning, because it is a cosmological model in development. Right now, there are key ingredients which still need to be worked out. I don't see fine-tuning problems right now. Now, you ask whether what string theory says about dark matter and about dark energy. See, dark matter, we have particle physics candidates for dark matter. And a person sitting very close to you can tell you a lot about that. So in the same, these particle physics models come out of string theory. So dark matter has an origin. Dark energy is a big mystery. The only thing we know about dark energy is that we know nothing about dark energy. And so far, string theory has not taught us anything about dark energy. But if there's any theory that exists that will tell us something about dark energy, it will be string theory. I can tell you why.
That's a challenge, huh?
Second thermodynamics law.
The second law of thermodynamics.
I'll pass on that. You come to me afterwards.
Maybe take the question there.
Hello. Yes. Thank you for your lecture. I have two questions. The first question I want to ask you: what do you think of the cosmological argument? Basically, as you know, before there was the materialistic view, which says that this world was infinite, and then there's now what we know as the Big Bang, which you are talking about right now, and that says the argument basically says that everything that has a beginning has a cause, yes, and if the universe had a beginning, and therefore it has a cause, and this cause should be immaterial, since it caused this material world.
Okay.
So that's the first question. The second question is...
Let me try to answer the first question.
Okay.
And in fact, in large part, I have to pass on that, because I think the question that you are asking is a question which ultimately is outside of the realm of physics. Now, what I try to show you is that in the standard Big Bang paradigm and in the inflationary paradigm, there is an initial singularity. So you can talk about a beginning. But we don't even know whether that's right, because in the stringy paradigm, there was no beginning. But there was an eternity going back in time. Neither of these avoids philosophical questions.
Yes. So this is my question is that the second question is, if it's in the string theory that it's eternity, now doesn't, like you said, it goes into the philosophical realm, and doesn't this basically says that if this is true, that it's eternity, that means we don't even exist, in the sense that, like the domino theory, basically saying that why did this domino fall? Oh, because this other domino hit it. Okay, why did that domino fall? Because that other one. So we'll keep on going. But if we keep on going and there's only dominoes, then no domino will fall. So basically, if you go eternity, then where's the first cause?
Right. So these type of questions I have not addressed at all in the talk, because they go beyond the mathematical scientific approach. So that's all I'll say now.
Hello, Professor, and thank you for your excellent talk. I have one question about the string cosmology. You talked about that there is actually no Big Bang 13 billion years ago, and
There's
only
no singularity.
and only the decay or the interaction of strings that actually caused them to expand. But what actually caused these strings to decay or to intersect? And why does it happen exactly at 30 million years ago?
Okay, so I mentioned that string cosmology is a theory in development, and you've touched on one of these issues. So I would have to actually say that one possibility is that the universe had first a contracting phase, and then this long phase, and then at some point the strings will eventually meet, and then 3 dimensions can become large again. But I do not have a mathematical, I don't have equations with which I can really convince you.
Professor, how much do you think is the probability that the superstring theory will finally make sense and become the theory of everything?
Okay, that's an ambitious question, and I want to give a very biased answer to that question. So I will say that we have fundamental questions in cosmology, and I think we will only be able to address them if we use ingredients of string theory. I'm hopeful that we will be able to verify predictions that were first made with string theory. Will this prove string theory? No. But it will show that string theory is really part of physics. But maybe, I've noticed one thing. So far, all the questions have come from men. What about the question from a woman?
There's few women in the audience, right?
No, there are a number.
Actually, I have 3 questions.
I don't think the microphone is on.
Okay, may I just speak now?
Okay.
Go ahead.
Excuse me. I have actually 3 questions. One is that, Professor, when you introduced the string theory, you mentioned that it makes it testable. What do you mean by testable?
Okay, the question was, what do I mean when I say a theory is testable? I'm going to take the theory, I make predictions for something that has not been observed yet. And then I make predictions for something that can be tested. That's what I mean by testable. So concretely, I presented to you a prediction for the spectrum of gravitational waves. That's an example.
In the back there.
Thank you for the lecture. I have a question on the specific slide of your PPT, which on the big piece is 3 pages. In the graph, you show, I think, this asymmetry between the before the Big Bang and after Big Bang. So I want to ask, since after Big Bang we have a large expansion, so can I say before the Big Bang there's a large collection or something like that? Or in another way, is there also a symmetry world before the Big Bang? Thank you.
You mean in the context of the string cosmology or in general? Yeah, so first of all, in standard Big Bang cosmology and in inflationary cosmology, there was no before, because there was a singularity. In string gas cosmology, we really don't, there is an asymmetry, but we don't know, maybe the asymmetry is only a reflection of the fact that I didn't go far enough back. I don't know which of the two there is. Now, I do not know. I do not know. And I don't want you to come away from this talk thinking that you know. Just you should see that the question about what was before the Big Bang.
That's the art of asking good questions,
right.
not necessarily
Right.
getting answers.
But let me elaborate on, there are other models of cosmology which are not based, where you give up on Einstein's theory, and those predict completely symmetric cosmologies. Contracting phase, then some transition, and then expansion. Those are so-called bouncing cosmologies. And some people here are working on bouncing cosmologies.
So Professor Brandenburg, Robert, so quite a few women in the audience. None of you are asking questions. Are you Tsinghua women so shy? One other.
Okay. Okay. Thank you very much. I have not read this. The three-body problem.
Okay. I've never read it.
Maybe
Any other here?
Well, Professor, you showed us a model to simply explain the superstring theory. According to your show, you see
that's fine.
according to the superstring theory, everything is made up of string. And at the very beginning, winding string broke up, and you see the inflation begin, and the universe formed. So I wonder whether in our universe today there is still such string and such paper that is shaped by the string. And one day, if the strings broke up again, and whether there will be new universes.
Okay. So, yes, it depends on some detailed properties. It depends on some detailed properties of string theory. There is a possibility that there will still be today strings in our universe. They would be distributed as a distribution of string loops and long strings in a distribution that we can calculate. And we can look for these. For example, in microwave background maps, in large-scale structure maps. And in fact, I gave a talk earlier today at the KITPC about these. So it is depending on detailed properties of the underlying string theory, it is a possibility that strings will survive in our present universe.
Okay. Now, the last question. Okay.
Thank you. What an honor to have the last question. And nice talk. What do you think if you are right, or if the theory is right, there's no beginning? Then what about the end of time, or the end of the universe? And if there's possible for the universe to revert back to one stream or 1D, is it possible to maintain or to keep the information of the current universe back in that 1D?
Okay, so you're asking, well, what about the future of the universe? Now, you see, some aspects of this can be tested, can be measured. Observations tell us things. So, in fact, we've discovered dark energy. And if the interpretation of the dark energy measurements are correct, then it means that the universe will expand forever and will not contract. There'll be no reversal. And better observations will answer that question more reliably.